hello, welcome to our last session of the seminar, MPP seminar. Today we have Jonathan, and I will let Alex to introduce him because he knows him much better than I, and I think he will do a better job than I can.
Yeah, so it's a great pleasure to introduce Jonathan Weinberger, or Jonathan Weinberger, as we say in German. So, like I said, it's German originally. So Jonathan will strengthen our Fowler School of Engineering. I will not be the only theoretical computer scientist from fall onwards. We're very happy to have Jonathan joining us. He's an expert in programming languages, particularly category theory and higher category theory, which will also be the topic of the talk. You're currently doing a postdoc with Emily Real. Might be known to some of you, one of the rising stars in category theory, for her book, for her work on category theory, and also for giving lots of talks on interdisciplinary research. You will also strengthen our so-called kind of hot community. I think you've been working on some of the work that Mike Schumann has been doing with a frequent visitor to Chapman. And finally, maybe when I started my own PhD back a long time ago, I got into category theory because of Thomas Streicher, who's one of the leaders in type theory, and Thomas Streicher also was Jonathan's PhD supervisor. And I'm very happy about that connection as well. So please, go ahead.
Thank you. Yes, indeed. Great. Thanks, Alex and Jose, for the nice introductions. And I'm very happy to be here today and to be here very soon back again for the long run. So I'm going to talk about formalization of infinity category theory. This is based on various joint projects with other people: Ulrich Buchholz, Danny Gratzer, Nikolai Kudasov, and Emily Real. I guess given the kind of broader context of the seminar, at least some of you have had some exposure to category theory to some capacity. If not, that's totally fine. I'm going to start off with the definition first. So a category is a structure in mathematics which models composition in a certain way. So roughly it consists of, it's a structure C that consists of objects A, B, C, and morphisms or arrows that can go between these objects, like in the picture that you can see here. And we also have this composition operation that whenever we have a configuration of arrows or morphisms like that, we have this third edge, the composite edge. So we can compose morphisms much like we can compose just ordinary functions between sets, for instance. And we also demand that every object comes equipped with an identity arrow that indeed behaves like identity, so that if you compose your arrow with the identity on either side, it just does nothing. And moreover, composition should be associative. So it shouldn't matter if, given 3 composable arrows, we compose the first 2 and then add to that the last one, or kind of the other way around. And many popular mathematical structures do, in fact, form a category. So we have the category of sets and functions. We have the category of groups. So these are algebraic structures together with group homomorphisms as the morphisms. These are set functions that preserve the algebraic operation. Also graphs that maybe many people of you have seen before in some capacity, together with graph homomorphisms that preserve the edge relation. Those form a category. Also topological spaces together with continuous maps, like deforming the mug into the donut. Those form a category, and these will indeed be of interest today. But categories also play a role, for instance, in computer science. There's a way to do database theory in a very categorical way due to David Spivak from the Topos Institute. They play a role in programming languages and also increasingly in machine learning. which is a very exciting new field that I won't talk about today whatsoever, but I'm always happy to chat if you have questions about that. So a category you can understand as a kind of universe of mathematical structures. And there also exists a meaningful notion of transformational morphism between categories. So those are the functors. Those are assignments between categories that maps, objects of one category into objects of the other category, and similarly morphisms of one category into morphisms of the other category in such a way that they preserve the composition and they also preserve the identities. So that gives rise to a notion of morphism of categories, which is exactly given by these functors. So we should be able to assemble categories themselves into a new category where the morphisms are given by the functors. And indeed, we have the category cat of categories, which is like the universe of mathematical universes, if you will. And the peculiar thing is that if we fix two categories, C and D, and we look at functors from one into the other, that itself is not just a set, but it actually also turns out to be a category via the notion of morphism between functors. So if the functors are morphisms between the categories, and we now have morphisms between those morphisms, we can think of these things as higher dimensional or two-dimensional morphisms. These are called the natural transformations, and they are like a deformation of one functor f into this functor g. So those often are written with Greek letters phi, and they consist of families of morphisms f of x to g of x for all objects x, such that for all arrows f in the domain category, we get these commutative squares. So that's a kind of, that's a kind of way of transform one functor into the other. And that tells us that the category cat is first of all a category, but it's a category where the hump sets are themselves categories. And we can think of those as a kind of two-dimensional category. And that's a very compelling idea that you can in fact iterate. So if you think of this just kind of geometrically, intuitively, we have the natural transformations that are these two-dimensional cells, and we could think of even higher transformations from one natural transformation into the other, given by a three-dimensional cell, and you can iterate this into the infinite. And that very naturally gives rise to the notion of infinity category. Of course, if you really wanted to make this precise, this would demand a lot of thinking of you, because of course you don't want to just have all these data with no laws, because for one categories, you have an associativity law or a unit law, and you will also want to have this in every other dimension. And those laws, if you write them down, they of course depend on kind of the lower dimensional laws that you've written down before. So it's combinatorially very ambitious to actually make this precise. But this has a lot of applications, especially nowadays in various branches of topology or higher dimensional algebraic geometry, in computer science as well, in concurrency theory or rewriting or type theory, which is the focus of my talk today, but also in physics and quantum field theory or other branches in mathematical physics or quantum physics. So how can we, what's a good way to approach this kind of complexity? So one way to think about the situation in ordinary categories is just by thinking of composition as this algebraic operation. So I'm writing now the set of morphisms from an object A to an object B as this kind of set or type, A arrow B. So this is all, all functions, all morphisms from A to B. So the composition operation is something like this, just some function that obeys some laws. But in higher dimensional category theory, what often is being done is we're not actually thinking of these objects as algebraic objects with a lot of operations, but we're thinking of these objects as some kind of higher dimensional space, topological space, if you've heard the term topological or topology before. And in infinity category theory, we can express this higher dimensional composition in a coherent way as follows. So we can say for all f from A to B and for all g from B to C, which is the picture that we have here. We want to look at the set, or even better, the space of data consisting of compositions of f and g. And this space of data would consist of pairs like this, where we have this potential composite edge here. And we also will need to ask for this ensuing triangle that we would get to be filled by some kind of bounded surface, by a 2-cell, by some higher dimensional datum that actually witnesses that, oh, this triangle, it's actually a commutative triangle. It's the full triangle, not just the boundary of a triangle, which maybe doesn't commute. So this is what makes up our space comp GF. And now asking for this composition to exist will amount to ask that, first of all, the space is non-empty, but we don't want it to just be arbitrarily large. We want it to be as non-empty, but as trivial as possible. We want it to be essentially the point. And since it's a topological space, we don't ask for it to be literally equal to a point, but we ask for it to be contractible, homotopy equivalent to a point.
Can I just ask a question? Because intuitively, this means that this filler you put in the triangle doesn't have a hole. Is that right? Can I think about it like that?
Right. So yeah, that's one way to think about it. Yeah.
Yeah, but it's even more stronger, right? You only have one connex component because it's contractible to a point, right?
Yeah, so I guess there are two things at play. So first of all, it's kind of, we can look at these data here, right? And well, this triangle itself, will be something that is contractible to a point, but also the whole space will be something that is contractible to a point. And whenever, space being contractible, that's really what it means to be homotopically unique. Yeah, and we will see some more of that. Okay, great question. So we're in a philosophy seminar here, or partially a philosophy seminar. So let's take a step back. This kind of idea to replace algebraic structures with topological or homotopical structures really indicates some kind of shift in foundations. And in fact, a lot of areas in math today are really fundamentally concerned not with strict equality, but with equalities up to small perturbations or deformations, in a coherent way. So you could ask, what would we have to change in our foundations, or what should our foundations be if they were to respect these coherences and these homotopical structures just automatically, and not by encoding them in some way, because fundamentally set theory, it's like, it starts off with something discrete. And of course you can kind of emulate continuous structure out of set theory. But the language of set theory itself will not see that, because you can write down non-continuous functions or something like that, right? And to check that a function is continuous, it requires some work. So the great mathematician Yuri Manin, who passed away not so long ago, unfortunately, he has this wonderful quote from an interview from 2009, which is actually around the time that homotopy type theory really started gaining a lot of traction, interestingly. So Manin was really concerned a lot with homotopy theory. But this quote is very interesting because there's a line of quotes from different people from different communities, some more from logic, some more from homotopy theory, but they kind of see the same thing. So in the quote, he says, instead of sets, which are like clouds of discrete elements, we envisage for these new foundations some sorts of vague spaces which can be severely deformed, map one to another, and all the while the specific space is not important, but only the space up to deformation. So he makes the point that it shouldn't really matter so much, you know, how do I write down the circle kind of in the Cartesian plane as some kind of subset, blah, blah, blah. But I'm really interested only in the homotopy type, like in the equivalence classes of all the homotopy equivalent spaces. And he goes on, I'm pretty strongly convinced that there's an ongoing reversal in the collective consciousness of mathematicians. The homotopical picture of the world becomes the basic intuition rather than the set theoretic one. And I think, I mean, yeah, there are all these areas that I mentioned that really have profited from this. I mean, homotopy theory, there's, I mean, homotopy theory and algebraic geometry in the work of Peter Scholze, for instance, a very young Fields medalist working in arithmetic geometry, so kind of the geometry of numbers in some vast sense. They have been developing theories where without infinity categories, it's either not clear or sometimes even not possible to capture certain phenomena. I mean, you can kind of capture the shadows of these phenomena, but not the phenomena as a whole. So this is not just abstraction for its own sake, but it actually arose from actual mathematics, you know. So we can ask now if we could replace traditional discrete foundations by new continuous foundations, or in other words, analytic foundations, where we have to build up a topological space out of, you know, some set, which is a discrete thing, together with a set of subsets of that set, the set of opens, which is again just the set, so again a discrete thing. So in these analytic foundations, we would build up all the continuous structure by something discrete. So in that sense, they would be considered analytic, versus the new continuous, natively continuous, or in other words, synthetic foundations, where the basic objects would just be already some kind of space. And in fact, there is such a theory, there's at least one, and that is called homotopy type theory, or HOT. And there exactly the fundamental objects are spaces up to homotopy. And this has at least two really practical benefits. So first of all, it turns out that some of the classical proofs from homotopy theory done in these new foundations are more intuitive, kind of more conceptual in some sense, than if you would do them, you know, in all levels of detail in classical set theoretic foundations. And actually, this theory is also particularly amenable to computer formalization, which is something that the computer scientists like and the philosophers should like as well, because it says something about the epistemology and maybe also the ontology of mathematical objects, maybe. So in terms of infinity categories, those objects have been around since the 70s, and so the notion was coined by Boardman and Folk. And they were really only extensively developed sometime later in the 90s and early 2000s by André Joyal and Jacob Lurie, and then by a lot of other people kind of in parallel and in the successive years as well. So this is really a kind of far-reaching business, you know, infinity categories of all kinds, and with various descriptions. But something that we can note compared to one category theory, or even, I don't know, two category theory, or n category theory, or finite n, the development is highly technical from the get-go. So even basic notions, I mean, I told you on the, I guess, second slide what the category of categories is, right? So with just having given the definition of category one slide before, if you really want to know what the infinity category of infinity categories is, which is just the infinite dimensional analog of this object, in this book, Higher Topos Theory by Lurie, which was like the first or maybe the second standard textbook reference on that subject, you would have to read up to page 150, roughly, to see the actual definition of that. And similarly, or kind of even worse with concepts like limits and co-limits or adjunctions, which are, I don't know, in a standard course on category theory or categorical logic, you would learn about them, I don't know, maybe close to half of the semester or something. In higher topos theory, you have to read about 300 pages. Just because in the higher dimensional setting, it's really all much more difficult. So this presents a high entry threshold for researchers, first of all, and even worse for undergraduates. So these infinity categories, I mean, they play a certain role in higher dimensional geometry, and there people often just want to compute certain invariants of certain spaces, and they're not necessarily so interested in doing category theory for its own sake. So what are they going to do if they want to use the machinery, you know, to actually compute something? So that's kind of a problem. And that has to do, obviously, I mean, or maybe not so obviously, but one stance that one could take is that it has to do with the fact that just that set theoretic language doesn't really deal well with the principles. So in infinity category theory, your category doesn't have a set of objects. It rather has a space of objects. And everything that you can write down, it should be automatically homotopy invariant. All the equations that you're really interested in, they're not equations. They're higher dimensional equality, you know, higher dimensional homotopy equivalences. And of course, the more technical your development, the more error prone it will be. So there is this interesting case, which is some work by Vladimir Voivodsky and Carlos Simpson, who had a paper on infinity groupoids from the early 90s, and around 7 years later, so this was Voivodsky and Kapranov, sorry. So that was their original paper, and around 7 years later, Carlos Simpson discovered an error, and Voivodsky for a long time, I think, he couldn't figure out what the alleged mistake in their original work was, but he also thought that Simpson's counterexample looks completely correct to him. But this counterexample would contradict his own work from before. So what are you going to do? And it took until 2013, actually, until Voivodsky was convinced that, okay, it actually was them who made a mistake. And that just had to do with, you know, this being just very complicated mathematics. So homotopy type theory, I'll say a little bit more in a second about what that is. It's a alternative foundations of mathematics, which is particularly amenable to doing synthetic homotopy theory, but also other kinds of mathematics. And higher category theory has these close ties with homotopy theory. So you could ask the question, oh, can't we use the development of HOT for infinity categories? And it turns out this is harder than expected. So HOT deals very well with actual spaces, which are essentially kind of these things, these like blobs that have paths in them between points. And a category is kind of similar. It also has these objects or points that you can draw an arrow from one to the other, but not every arrow typically is going to be reversible. So not every arrow behaves like a path. And that's a big problem if you want to try and develop this theory in homotopy type theory, but it's possible, and that's exactly what I'm going to talk about today. So I'm going to introduce the basics of homotopy type theory and then the basics of an extension of homotopy type theory that allows us to talk about infinity categories. And then, depending a little bit on time, I can introduce some parts of the work on the formalization of what's called the Yoneda lemma in that setting that we did. So the Yoneda lemma, you can think of this as being like the fundamental theorem of category theory, really. And so I mean, there is a version of this, you know, just in the type theory, and then there's an actual computer formalization. Okay, so that's the recipe. And if another question comes up, feel free to just interrupt. So homotopy type theory, it's a relatively new field that has been sparking in the early 2000s, and it's still very actively under investigation. And it goes back to something kind of classical, namely Martin-Löf type theory, which is a constructive version of type theory in the 70s. So type theory is a kind of, in some sense, it's a kind of style of formal or logical languages which unify the object with the meta level. So in a type theory, you can capture the objects that you want to talk about, like sets, but you can also at the same level capture the logic that these sets should obey. And we will see some of this play out very nicely. So Martin-Löf is this logician philosopher who's been later doing work on statistics too. And he was interested in constructive type theories with the well-behaved notion of equality. Basically, they should obey Leibniz's law. That's what gave rise to Martin-Löf type theory. And a fragment of this, for instance, is lambda calculus. But Martin-Löf type theory is more expressive than that. And due to the work of a number of people that I've listed here, still not exhaustive, but those are all very important steps along the way. In this millennium, it has been found that there are striking connections to topology, namely that the kind of you can give very canonical interpretations of this type theory into homotopy theories, essentially. So that means that everything written down in a type theory like that can be read as statements about topological spaces and not just sets and propositions, but actually, infinite dimensional geometric objects. And one of these people, very notably, was Vladimir Voevodsky, Fields medalist in algebraic geometry, motivic homotopy theory. So also someone not coming from logic, but who at some point after getting his Fields medal, or at least that's when it intensified, really turned into trying to think very hard about foundations of mathematics, and he learned to use the proof assistant Keck to verify statements in piano arithmetic, and that's someone who did this very abstract, these big breakthroughs in very abstract algebraic geometry and number theory, suddenly turning into someone very very attentive to logical foundations and questions of consistency using the computer. And he worked out basically this interpretation of Martin-Löf type theory into these objects called infinity groupoids, which are like infinity categories, but we can actually invert every arrow. And infinity groupoids that was known to the topologists for a while, those can be seen as topological spaces up to equivalences of their categories. In fact, this paradigm and its generalizations are known as Grothendieck's homotopy hypothesis, and I'm pointing this out to allude to the Grothendieck conference that took place here at Chapman not so long ago, where this certainly also played a role. Okay, sorry about that. So I also want to point out the homotopy type theory, that's really a new field. So the community is also relatively new, but it has been very active. So the first textbook that got written on homotopy type theory is this one. It's a free and open collaborative project by a big team of authors and associated contributors and accompanying formalizations. You can find it all on GitHub. So that was written during the special year on homotopy type theory at the Institute for Advanced Study in Princeton. And there's a second textbook now by Egbert Reike called Introduction to Homotopy Type Theory, to be published at some point soon with Cambridge University Press. And if you want to get really into it, I really recommend looking at the website from the hottest summer school. So hottest, that's an ongoing seminar on homotopy type theory from various perspectives. So it's arguably more of a research seminar, but they had this online summer school in 2022, which was a really big endeavor. And all of the resources are still available. So there's tons of lectures and tutorials and also research talks, but in particular, really, you know, like complete lectures by experts from the field on YouTube still. Everything is available, formalizations, talks, and slides. And we still have the Discord active with, I think, more than 1,000 members, where you can ask questions, and surely someone is always going to be answering. So yeah, so it's a community that I'm very happy to be a part of. It's very welcoming and very resourceful and friendly to everyone interested, no matter what the background is. So so there have been effects that people really coming from software engineering or computer science, they started reading the hot book and they started engaging in this community, and they hadn't known about homotopy theory before, and suddenly they were formalizing their own proofs, you know, about homotopy groups that that are usually part of the classical literature on algebraic topology, and they were able to develop their own intuition without really knowing what a topological space is before. Which is quite interesting from many viewpoints. And there's this blog here and also a Zulip chat where you can also engage actively. And of course, there's also a lot of philosophical literature on type theory and category theory. So here I've named some, and some of these books are really very recent, like all those ones. For instance, I guess Rodin's book also hadn't been, has been published not too long ago, and they contain very interesting reflections on kind of synergies between type theory, philosophy, foundations of math, category theory. Okay, so type theory, what does it consist of? So, in set theory, typically, the basic objects are sets. And then sets can have elements, but these elements, at least the way that it's usually done in ZFC, let's say, these elements are also just sets. So you really have only one sort. Everything is just a set. And that's kind of not so natural, because we want to say, oh, we have the set of natural numbers, and the number 3, that's a natural number, but it's really not itself a set. So, okay, then maybe you might start thinking about ordinals or something, but at least for many purposes, the actual implementation is not really in line with the intuition. And in contrast, in type theory, you have this fundamental distinction between you have types written in blue, and then those can have terms written in orange. I'm hoping that is that like visibly well on the screens with the contrast. Okay, I'm never quite sure. So you could also think of like how in a programming language, you have the type int of integers, and then 0, is a term of that type. So those are kind of the basic elements that we start from. But now we also want to be able to look at families of types indexed by other types. So we might have an indexing type A, and then we might have a family of types. So a collection of types, B of A, indexed by all the terms of big A. And that's what gives us what's called dependent type theory. So types can now, or type families can depend on other types. So the terms dependent type and type family, I'm using those synonymously. Okay, fair enough. So now in math and in logic, we're always interested in performing constructions. What constructions can we perform here? We can perform the Cartesian product, so we can look at types of pairs, and we can look at types of functions between types. And those also have a dependent version. because we're in dependent type theory. So, so the dependent version of the pair types or the product types are called the dependent sum or sigma types or dependent pair types. And those also consist of pairs A, B, where A is from, sorry, the first element A is again from the type A down here, but then the term B, that's a type from, that's a term that somehow comes from the dependent type B, and it has to come from the right member of that family, right? So it has to come from the type B of little a. And likewise, the dependent generalization for functions would be a dependent function. So it would, let's say we have a term x right here, and we look at a dependent function, and that would assign to every x in A some term in B of x, some term f of x. So first of all, we can look at these dependent these dependent pairs and these dependent functions, and those also will assemble into types themselves. And geometrically, you can think of this as in the situation of dependent sum types, you can think of this as kind of taking the sum over all these fibers, over all these members in the family, kind of summing them together, in an index way, depending on the indexing type that you have down here. And in the topological picture, this amounts really to taking the total space or the total type of that family. If you have seen, I don't know, fiber bundles in topology or something like that. So that's really the intuition that you can have here. Or just the disjoint sum, for the set case of all the pre-images or the fibers of a given map. That's the same intuition. And the sections, likewise, they assemble into this pi type or dependent product type. And these sections, once again, if you've seen some differential geometry, they're really like the sections of bundles in that sense. Now, there is this peculiar thing called the identity type in Martin-Löf dependent type theory. So we have these distinctions between two kinds of equalities. So first of all, we have judgmental equality, which is rewriting one term into the other term by some rewrite rule that we're given in the theory. And those are kind of the trivial rules, if you will. I mean, the trivial equalities, because you don't have to do anything. You just have to, let someone apply the rule and then rewrite it for you. But you don't have to come up with that's at least one way to think about it. But then you might also want to keep track of identifications that are not strict, that are more like paths, going from one point to the other. Like if I'm
can you write on this part of the
yeah, I'm so sorry.
yeah, it's fine.
Yeah. So if like my type or my space is a kind of blob like that, and I have 2 points here, okay, those are not judgmentally equal, but they have a path P. And the way to reify this is via Martin-Löf's identity type. And this comes, so that's also a dependent type, because it's actually a family of types that depends on the points, on pairs of points on the space or in the type. And of course it should come with these canonical reflexivity terms. So every term is equal, everything is equal to itself, right? And this is tracked by these reflexivity terms. So we have a term reflex that witnesses an equation or an identification of x with itself. But then there might be other identifications. So a point might have more than, might have some non-trivial loops. And then there might be non-trivial, there might be non-trivial connections between points that are not equal. And okay, this is something I don't want to get into detail too much now, but to kind of complete the rules of this identity type and to make the Leibniz equality work as it should. So if two objects or 2 points are kind of, or 2 terms are equal or equivalent, then it should be true that if a statement holds for one term, it also should hold for the other term. And this principle is reflected in this elimination principle here, which tells us how, which essentially tells us how to generate, how to get sections in a family that depends on a path by just knowing, or by just prescribing values to the section on the canonical reflexivity term. And that's a very important principle for various reasons. It allows us to prove a lot of things. So I don't want to get into the weeds here, but one more or less immediate set of consequences is that it endows the type of identifications with the structure of an infinity groupoid. So just having this principle gives us inversion, so every path can be reversed. It also gives us compositions, so paths can be composed. And it also gives us the kind of expected laws about these compositions and inversions. But note that again, these, such as associativity of these paths, that doesn't, that's not a strict equality. That's again some higher dimensional identification. So we can produce a term in an identity type over identities or over identifications. So these groupoid laws only hold weakly in a higher dimensional sense, so they give rise to an infinity groupoid structure on these families of identity types. So if we have points x and y here, and we have paths p and q here, we can have higher homotopies between these paths, phi, and then homotopies between those and so on. So yeah, again, I've said that the dependent types, they can be viewed as a kind of fibration, which is like a space parameterized by a base space like that. And we can also lift paths, which again is also something you can think of it as a topological version of Leibniz's law. So if you have an identification between x and y, and you know that p holds for x, also p holds for y. That's a logical way to think about this. But it's also reminiscent of this geometrical picture that you see here, that you can lift paths in the base to paths lying over it. It's called the path lifting property in topology. And there's a kind of a stratification of models that you can look at. So you can interpret all of these type formers like in the sense of predicate logic, but you could also interpret them as sets, which is kind of one dimension up, or you can interpret them in the sense of homotopy theory, where you go from propositions to sets to spaces, essentially. Okay, so I gave some philosophical motivation, and just to give a picture how this kind of can play out. So if you think about how to define the circle in traditional foundations, okay, maybe you're saying, okay, it's exactly all the points that have distance 1 from the origin. Okay, so this gives you that. But in homotopy type theory, you're defining the circle as the type C that consists of some point B, which is like the base point of this circle, and then a loop, so some path, some self path from B to itself. And you're asking that the type is kind of freely generated by this data in some sense, which you can make precise, which I'm not going to do here, but that's a perfectly good definition of a circle in homotopy type theory. and it has various advantages. So you don't have to think about encoding. You don't have to, it's more intrinsic. You're thinking, it's more like you're encoding the space by exhibiting, oh, what universal property should it satisfy in a homotopical sense. Whereas here, I'm not saying this definition is completely useless. It's obviously not, but yeah, it's of a different flavor, I would argue. One can have more discussions about that, but that's just a compelling example to show.
So do you need the homotopy type theory to get the universal property, or only to simplify matters?
I mean, the way to define objects are kind of all gonna be something like that, if that makes sense.
And then you use path induction to get the universal property, is that right?
Yeah, so yeah. Okay, so the universal property, together with everything satisfying path, I mean, with the identity, the homotopy, the identity type satisfying a path induction, that will give you very nice proofs. You can transport loop, you can transport like points along loop, something like that. So yeah, we can have more discussions about this, but this is kind of the way to really define the primal types. And that's also something that you have to postulate that this type exists. You can't derive it from the axioms that I showed you. You have to postulate because it's a new type with a new induction principle, not something that can be proved out of what I showed you before.
What is the induction principle?
I'm not going to write this down, but it's but it involves it involves these data. Yeah.
And just to stick on this one question, with the definition on the right, is the details you're not giving us the metric information about the circles in that.
Yeah.
Because the way you're presenting it, it just looks like it's purely topological.
Yeah, that's a great question because it's also not metric. Yeah, exactly. I'm not defining a metric. That's great. So here I'm really defining a metric space, and of course that's going to have a homotopy type. But here I'm not defining a metric space at all.
So then it's not quite a circle. It's
that's
just
right.
Topological.
Yeah,
up to homotopy.
It's the homotopy type of the circle. Yeah.
Okay.
So yeah, exactly. Yeah, great. Yeah, great observation. And that's really what in homotopy type theory. It's really, you have to do it that way, because every type is only because the theory is homotopy invariant. So in the standard theory, you shouldn't be able to distinguish between two models of the same homotopy type, because that doesn't, that would just break the homotopy invariance. Yeah.
So now after John's question, I have now.
Sorry, sorry.
So what if you want? Oh.
No, go.
What if you want to do metric stuff in homotopy type theory? Can you do that at all, or does it get crazily complicated, or is it actually kind of not too bad?
Yeah,
that's exactly the same question that me. I formulated in another way, so there is only one answer. In this way, you cannot distinguish between circle and ellipses. But if, of course, this is a very interesting theory in which you do not distinguish. For example, in projective geometry, you do not do that. But one thing is not distinguish a circle from ellipse in a particular theory. Another is not to be able to do it in a foundational theory. So what does it mean to have a foundational mathematics where this distinction is not possible to be done?
Yeah, I mean, okay, great question. Let me just answer with kind of pointing out a reference. So breaking continuity is possible in something called spatial type theory. And that's something that has, that's a modal, it's a modal extension of homotopy type theory. It has been proposed by Mike Schulman, and he has a great paper from around 2018 on Brouwer's fixed point theorem. In that extended setting of spatial or or more generally, I mean, there's a more extended story called cohesive type theory. So that goes back to Lavier and Schreiber. And actually, David Corfield has a book where he discusses the questions that arise from a philosophical point of view about this. So that's also linked on the slides. Yeah, so basically you have to introduce another layer where dependency is discrete rather than continuous, and then you can do some things. But yeah, this theory, the way I'm talking about here, I mean, you have a way to talk about sets, but it's also, I mean, there is some, you can talk about discrete objects, but the ambient theory is still continuous and homotopy invariant. Okay, so now coming back to infinity one categories, just real quick, what we want to do is we want to be able to do composition in that way. So we want to be able to capture these composition data. How could we do this in homotopy type theory? Well, first of all, we know roughly what these path types are, but what about Hom types? What about directed arrow types? And there are several frameworks that deal with that due to various people, and it's still very much an ongoing field of investigation. But the connection of many of these theories, these directed type theories that have this like sense of direction built into them, their connection to infinity category theory in the sense of homotopy theory is not so clear. But there is at least one theory where it's been proven to translate in the right way to like traditional infinity category theory, traditional set theoretic infinity category theory. And this is Emily Riehl and Mike Schulman's simplicial extension of type theory. So simplicial means it has to do with simplex, so with triangles or pyramids or higher dimensional versions of this. And that's exactly the theory I'm using in my work with my collaborators. And I'm also using kind of heavily ideas and methods from Emily Riehl and Don Verity's infinity cosmos theory, which is another way to do this synthetic infinity category theory, but based on set theory and kind of doing the formal, what's called the formal or the Australian style category theory of higher dimensional categories, but influenced by set theory. But interestingly enough, these theories, they have some common like intersection in their development, and there have been various instances where one influenced the other. Yeah. Okay, so roughly what this is, well, first of all, we're adding kind of shapes to our type theory. It's these simplicial shapes. So like the point, the directed arrow, the two simplex and the boundary of the two simplex, and kind of these sub parts of the boundary like this horn, so the pair of two composable arrows. And then we're adding another gadget called extension types. So those maybe are at first glance a bit complicated to understand, but basically they're a general schema to allow us to define Hom types or arrow types. So an example where this plays out is, or the actual definition is given as follows: assume we have a type and two terms in that type. Using these extension types, which are written with these angular brackets, we can first of all look at all the functions from the arrow into the type. So those are just all arrows at B. But we want to not just look at anonymous morphisms, we want to look at morphisms from a fixed A to a fixed B. So these extension types allow us to restrict the values on the boundary exactly to A and B. So that's what they are for. And we can also do a dependent version of this, where we look at maybe a picture like this. So what we want to do is, let's say we want to look at an arrow like that, with points lying over the endpoints of that arrow. And now we want to look at all the arrows here, kind of going from one fiber, going across the fibers in the total type that project down to this arrow here. And that's what these extension types are doing. And we can also do this for more intricate shapes, like we can fix a triangle here and then look at like a horn like this, shaped like that, or a full triangle lying over this triangle or something like that. So this is all kind of the stuff that one needs in higher category theory. And there's a very simple definition now what an infinity category is. So it's something that should have this weak composition operation. And in set theoretic foundations, this would be an infinite set of conditions that maybe somehow cohere with each other. But here, because, here it turns out that we really only need to consider a single condition that only takes into consideration data of dimension up to of dimension up to 2. And it generates a condition in arbitrarily high dimensions, and it's exactly the right condition, which is not at all trivial to show. So it goes back to some work that Joyal did, maybe together with Tierney a long time ago. And this kind of harmless looking condition, it just says that, okay, the pair of composable arrows in the type, it looks like the type of the 2 simplex. That's what that said. And to get actual infinity categories, we have to add another condition that tells us that the isomorphisms that are derived from the directed arrows are, coincide in a certain way with the path types. And if we replace isos with directed arrows, we get infinity points. So that tells us every arrow is invertible. And that condition, interpreted in the homotopical sense, gives us the correct coherent version of infinity points. So yeah.
Can I just ask her? So Joyal did this earlier, and this was, but then he had to do it in set theory, and that was complicated.
That's right.
And now you're saying you can do the same thing in hot, and now it's basically just this one condition.
Okay, so what Joyal showed, he showed that if you look at this equivalence here, and interpret it in set theory, Joyal showed that in set theory, it's enough to just look at that condition. Because this is an internal condition. Now I'm saying internal, all interpreted in set theory, but now it's internal exponentials and bisimplicial sets or objects. And that somehow generates all the conditions on the, I guess, the simplicial, on the set level. One way to say that. And the point is, if you know this, if you use Joyal's result, you can kind of take this, and then it's clear, it translates, you can take this, translate it into the external statement, which is just, okay, read everything, all the symbols that you see here, replace them, by the sets that they interpret to. And then Joyal's theorem tells you, oh yeah, okay, you're done. But what's more so actually is that kind of internally, and this wasn't known before because there wasn't such a language, so it didn't make sense to phrase this. Internally, it also gives you all the stuff that you want. And I think we have a proof due to Tashi Valde that maybe also has been formalized, that you can show internally that this generates also the higher compositions. I think he did this last year at some point. So, okay, there's a bunch of results that tell us that this actually translates to the right version of infinity category theory, and not just infinity category theory, because Mike Schulman showed in 2019 that not just spaces, it was shown before by Wygotsky, and other people that work on that too, that spaces are a model of homotopy type theory. But Mike Schulman completed the proof and introduced a new framework to deal with the last remaining issue, which was very complicated, about universes. So essentially showing that every infinity topos, whatever that is, every infinity topos can serve as a model for homotopy type theory. And infinity toposes are, if you've ever heard of topos theory, which are these models for intuitionistic higher order logic, somehow there exists an infinity categorical version of them, and due to Mike's work, we know that they equally well serve as models as hot. Okay.
Does this bias something in terms of new interesting models we didn't have before?
Well, great question. I mean, maybe I don't know if I can give a one-word answer, but it's, I mean, it was a long-standing conjecture, and the point is that the class of infinity toposes were really supposed to be the standard models of HOT, essentially. And then, I mean, there's some, I mean, not all, I mean, there's obviously, I mean, some homotopy theories are different than other homotopy theories. So there's counter models to certain to certain theorems showing that, okay, something cannot be derived internally in HOT, so,
Yeah, so maybe it's not so much the individual models you get, but just conceptually that you're saying that this is what you actually always wanted.
Yeah, I mean, that definitely that, definitely
Okay.
that, yeah.
Okay.
There was, yeah, internal language, I mean, I think, yeah, all these internal language conjecture, yeah, was open for a long time. And kind of like one categorical level higher, so spaces are infinity groupoids, and infinity categories, are a generalization of that. So this shows, if you take Mike's result, together with some semantic result about the simplicial extension, this shows that we're not just dealing, like doing simplicial HOT, we're not just dealing with synthetic infinity category theory, but we're dealing with synthetic internal infinity category theory. So internal categories typically are maybe some kind of diagram or something like that. But here, now we can just treat them as types. So we're doing internal higher category theory, but in a way that really just looks like one category theory, not even internal, just one category theory, just homotopified. And in the higher categorical literature, I mean, there are all these kind of different models of infinity categories, which is another thing that sometimes can be confusing to say the least. And they're all equivalent in the sense that, they give rise to the same homotopy theory, but I mean, they're really very different categories and all stuff like that. And it's somehow not really possible in a rigorous way to do all this stuff in the way that you would want to do it. I mean, you would want to do it in a way of just doing, yeah, okay, I'm not for everything, but for a lot of things, you want to just do them kind of naively as you would do for one category theory, just kind of understood homotopically. And if you're very skilled, you can kind of just write it down without specifying too much which model it is that you're actually working on, and it can be made precise later and justified. But we really want a language that supports that. And this is such a language. And it's far from supporting everything that people have done or are going to be doing, and but it's definitely, it supports a lot of things, I would say, and it's also it's an ongoing project to support even more. Okay, so let me skip ahead some more. How much time should I take from now on? I think I started roughly now.
Yeah,
So so maybe like 3 minutes from now. Is that?
Yeah, that's 5 or
fine?
10.
Okay. Right. Yeah. So I mean, there is also this work on cubicle type theory that Thierry Cocon was, I mean, among other people, but he was one of the people behind this from the beginning, which was the endeavor of coming up with a more general system which interprets homotopy type theory, but in which you can prove this univalence axiom. So Vygotsky's univalence axiom tells you that homotopy equivalent types are actually equal in the theory, propositionally equal. And that's an axiom, but in type theory, we don't like axioms because they don't compute. So we want a different type theory, ultimately, in which you can prove this axiom. So we only want to have some, a system with rules, but not with axioms. And there is an intricate connection also between simplicial type theory and cubicle type theory. So there is some work. So I mean, simplicial sets are sets parameterized by simplices, so like triangles and pyramids and everything. And cubicle sets are sets parameterized by squares and cubes and hypercubes and so on. And there's an intricate relationship between those two topuses. So there's some work by Kapulkin, by Wodzki, Christian Sattler, some of it together with Evan Cavallo, but also from Thomas Streicher and myself, that show how cubical sets embed very well into, simplicial sets embed very well into cubical sets. And this is actually crucial for the internal treatment of universes, which is an ongoing project where we have made a lot of progress in the recent past with Ulrich Buchholz and Danny Gratzer. And that's something that ultimately, I mean, it changes the category, but in such a way that it gives us new constructions that we can just perform again on the simplicial level. So, and these universes are essentially things like the infinity category of infinity groupoids or of infinity categories. So those get essentially the fact that, you know, or the ability to even construct or reason in a fruitful way about them, that's something that we need this embedding into cubical theory for. But that's not at all what I'm going to talk about today. So, so something to be recorded is that, I mean, the theory of functors and natural transformations, kind of the very basic thing from infinity category theory, that behaves really well inside this synthetic infinity category theory. So every map between two types that happen to be infinity categories automatically respects all these functor laws. Again, these are identifications, so not strict equalities, but weak equalities. But, you know, it all works out the way it should. And you automatically get the right kind of definition of natural transformation. You just get it out of the behavior of these extension types, which is also really nice. I've said before that every type family has, you know, behaves like a fibration. So in the sense that we can lift paths, or we can kind of transport, if we have a path in the base, we can transport a point over A to a point over B. We can now ask, is this possible if we replace paths by directed arrows? And it turns out that it is possible. So Emily and Mike, did some work of this in the case where the fibers over the base category are groupoidal. And together with Ulrich, and then in some of my own follow-up work in my thesis, I've generalized this to where, you know, the fibers are categories, or where maybe the kinds of dependencies are more intricate. And that's also the story where the Uneda lemma comes in. So the Uneda lemma tells us that, or one way to say what it is that assume you have a parameterized object. So here, kind of for the purpose of presentation, I'm assuming that the family is parameterized by arrows starting from a fixed point. Then if I want to look at the sections, or the natural transformations, if you've seen the Uneda lemma before, the natural transformations from a representable into the family, those you can identify with just the value of the family at the point, or at the identity. And we have a bunch of Uneda lemmas exactly for the situations that you would expect. And interestingly enough, which I don't have more time for this, but you can view this very analogously to path induction, this identity elimination principle that I showed you before. But this is a directed version, and it's kind of, yeah, anyway. And I mean, so this is not universally true. This is only true for certain kinds of type families. So specifically in the case that I'm talking about today, we want to look at covariant families. So for a covariant family, those are essentially a way to encode presheaves without saying what the infinity category of groupoids, or which is like the analogous thing to the category of sets is. The property is the category is called covariant or discrete if given an arrow in the base and a point X lying over the initial point here, I can, up to homotopy, uniquely lift this arrow to an arrow that lies above. So the space of all this data is contractible. That's what a covariant type families, and essentially it models a covariant presheaf. But I could also do, I mean, I could kind of reverse this direction, and then I would get the usual contravariant version of presheaves. And okay, this satisfies all a bunch of laws. It's all well and good. And in particular, it satisfies the Uneda lemma. And what's very interesting now is that proving this Uneda lemma, which is a statement about infinity categories, it translates to a statement about infinity or internal infinity categories with respect to an arbitrary ambient infinity groupoids. This theorem, proving it internally to this theory, it's easier than proving the one categorical Uneda lemma for one categories, because essentially we get a bunch of naturality properties for free. Like in the standard Uneda lemma, when we want to define this map, we kind of have to say, okay, I'm mapping something to something here, and then I have to show that this is like a type of natural transformation. So I have to show that it actually gives me a natural transformation. But here, I just have to give a term that type checks in the sense of that it lands here. And I know in general that this already is a type of natural transformations, and then I'm done. But that's just part of proving the Uneda lemma. I mean, you have to prove kind of like that those two maps are inverse to each other, but that's not at all that hard. And it actually has been formalized. So there's lots of things about formalization in general that we can say, but this has been formalized in the RZK proof assistant. So that's a new proof assistant for the synthetic infinity category theory developed by Nikolai Kudasov from Innopolis University. And it's the first proof assistant with an actual existing library that we developed in the course over the past, basically since, I guess, February last year. Initially together with Nikolai and Emily, but then a lot of other people joined and can still join today and contribute all sorts of things. So, so this is all open source and free, available on GitHub. We have a VS Code plugin that works really nicely, and we also have a Zulip chat where you can kind of join us. And the nice feature is that you don't only have kind of this code that encodes these algebraic notions, but we also have a generator that, at least in some cases, is able to generate these simplicial shapes, telling you what's going on in your code and what lifting and filling problems you're currently dealing with. Here are a bunch of references. I specifically want to highlight Emily's paper that appeared recently in the notices of the AMS. That is a very nice philosophical, mathematical discussion, kind of starting from the question, could infinity category theory be taught to undergraduates? Kind of making the point that if in 100 years worth of time, you know, we have all accepted the basic notions of univalent foundations and homotopy type theory, homotopical foundations, then infinity category theory really becomes like, you know, amenable to like the first semester or maybe the second year, because it's just all going to interpret into the right thing because we've chosen the right language. Thank you for your attention.
Time for questions. Okay. Peter?
Can you say a little bit more about the modal extension of HOT? What exactly, why is it modal, and how, how should I think about this in relationship to ordinary HOT?
So ordinary HOT you can think of just spaces where everything has to be continuous, in particular dependency has to be continuous. But if you want to do non-continuous things just on the set level, I mean, you really have to add something, because it's just, you can't do it, you know, it's too restrictive what you have. And that's what the spatial part of spatial type theory adds to you. And okay, when I say modality now, maybe it doesn't mean a whole lot per se, because modality could just mean it's an operator on the universe. So it's a, you know, it's an operator on your types. But you're not just adding an operator on a modality on your types, you're also modifying the way that your context works. You have to introduce a new kind of context, which is amenable to this, you know, non-continuous or discontinuous dependency. And then, of course, they have to interact in some way. And a lot of this is really influenced and works analogously to more classical kinds of modal logics that you and probably a bunch of other people here are aware of. So there's a lot of discussion about this. It's all still ongoing, you know, looking at these modal type theories or multimodal type theories. I guess David Corfield's book is a great blend of, you know, it also contains philosophy, you know, all these like classical considerations coming from philosophy, but also new ideas of Urs Schreibers, you know, Lavier, Mike Schulman, to kind of make this amenable to doing this kind of math that I talked about today, or like higher synthetic differential geometry, maybe amenable to quantum physics. I mean, that's something that Urs with his group is working on in Abu Dhabi these days. There's a lot more literature pointing out and discussing these various connections, but that's for now, that's the intuition I would recommend to have. Yeah, it's because we want to have different modes of dependency. Maybe a way to say that.
Ben?
Well, it may be related, and I'm not sure I completely followed you, but it sounded like one of the big overarching aims of your research is to shift foundations of mathematics from discrete to continuous. Did I get that right?
I guess that's a way to say it. So personally, I'm not looking for, I don't know, the one theory to rule them all or something. I just happen to be very interested in these homotopical flavors of math. And the reason why I like to work on new foundational systems for them is because I find the idea appealing, and also in practice to work out quite well, that it's often a better level of abstraction, because doing all this in set theory, it's kind of like, let's say you have a database that you're working on your computer, but sometimes you'll have to use assembler code, or you have to alter some bytecode manually or something like that. That doesn't seem like a good level of abstraction, right? If you just want to be dealing with databases, it's something much more high level, okay, something much more abstract. I want to use some domain-specific languages for my database. I don't want to write assembler. But doing infinity category theory in set theoretical foundations, in some ways, it's like exactly mixing those levels.
Mm.
That's an argument that I like to kind of point out. Because here the language just takes care of everything well, not everything, but it takes care of just working in the right level for you. And you just don't really see the encoding in such a way. Of course, it's still somewhat influenced by this encoding also, because in the simplicial type theory, I mean, it's also, you can also say, oh, you're emulating the structure somehow. There's also various degrees of syntheticness. So in this theory, maybe some have noticed, I still I said, okay, we have a type theory where we can talk about infinity categories. I'm now telling you when a type is an infinity category theory. And you might object, okay, so if you're defining what an infinity category theory is in your type theory, then your type theory isn't really synthetic for infinity categories, right? Because then that would mean that every type has to be an infinity category. It has to be an infinity category, right? So, and that's true. So it's not 100% synthetic for you know, or forget about the infinity. I mean, just even asking for a type theory where every type is a category, you know, just a one category, that could also be a question. And it is a question that people are thinking about. But if you did that, you would kind of lose a lot of properties of it wouldn't be like standard Martin-Löf type theory anymore. So that's why the theory I'm presenting, it's synthetic with respect to some certain thing, some kind of like two-dimensional space where one axis kind of gives you the categorical structure. But it's also not completely synthetic in the sense of, oh, my basic objects are the objects I'm interested in, namely infinity categories, because they're not the basic objects there. Because if they were to be, your type theory would have to drastically change. And there are also people thinking about these kinds of questions, but I personally just find this a good middle ground. But I also think there's a lot of value in thinking about these other more, you know, even more synthetic theories, if that makes sense.
Could you define what you mean by synthetic for? I think I got the idea from what you've been saying, but can you just make it precise for me?
Yeah, I mean, okay, I don't want to really define it because, I mean, if I gave you the definition that I think should be the definition, then I would contradict all my use of synthetic of the word. But I mean, synthetic in a very strict sense should mean that, you know, a theory is synthetic for X, where X is a class of objects, would mean that every object in that theory is, you know, is an X. So homotopy type theory, it's really a fully synthetic theory for homotopy types or for spaces, because every type is a space. But simplicial homotopy type theory is not in that sense a synthetic theory for infinity categories, because a general given type in that theory is something even more general than an infinity category. It's what's called a simplicial space. So it's like a space, but kind of even higher dimensional. So it's kind of like a two-dimensional space where you can look at what are the arrows in one axis. And if the arrows, you know, in that one direction in your space happen to admit this composition, plus also this completeness axiom that tells you that isomorphism is like path equivalence, then this space satisfies the property of being an infinity category. And that's very, I mean, if you want to read up more on this kind of more from the set theoretic point of view, that's what's called the Siegel space model of higher categories. And it's of course an internal, so this type theory it's like an internalization of that. But in that sense, it's not synthetic for infinity categories in the sense that homotopy type theory is synthetic in the sense of, you know, synthetic for homotopy types in the sense that every type in hot is actually a homotopy type. But here, in simplicial hot, every type is a kind of generalized space. And the kind of weird thing is, we're actually not interested in this. I mean, typically you're not really interested in just a general simplicial space because it's this super huge thing which you can kind of triangulate, but you cannot at all compose, not really, you know, only kind of very trivial things. But the point, so why, I mean, why are we even considering such a theory where we're only interested in a very small part of the basic objects? Well, because the ambient theory of those guys is still a topos. So we can do logic in a good way. So like sets or infinity groupoids, they form sets or spaces, they form a topos. So they are good for logic. But categories do not form a topos, not at all. They're very far. And that's just already not, I mean, that's something very intrinsic to categories, not just infinity or whatever. It's already not true for one categories for various reasons. But these Siegel spaces, I mean, they don't form a topos either, but simplicial spaces form a topos. They're just kind of some kind of diagrams in something that is a topos, like in spaces or some other anonymous topos. Okay, so that's just a presheaf topos. Okay, so it has a good logic. And I'm only interested in very specific objects, very specific presheafs. but the overall logic should still be a kind of familiar enough logic. And that's what I have here. Yeah.
So was this the proof of the Unida lemma on one of your slides? Is it that short or?
I mean, spelled out, it's somewhat longer, but it was an outline of the proof. So yeah. So the Unida lemma says.
So I would like to see the code in RZK.
Okay. Yeah, we can do that for sure. Yeah, maybe it's maybe better if I do it on the.
Yeah, but if it leaves us too far away, I mean, it's just that I've been looking at in the recent.
I should have a screenshot here where.
Weeks, and so
Yeah. So I mean, this is okay. Now you might say this is trolling a little bit. So I mean, this is kind of the code, but of course it uses something. I mean,
yeah.
So because the Unida lemma should say that two maps are inverse to each other. So if I'm composing I'm doing Unida after, okay, I guess we changed, I forgot which composition or order of composition that is. So anyway, one of the round trips doing Unida and then evaluation of identity. This EVIT is evaluation of identity. The Unida map, it's in our picture here, it's like this transport map because we're looking at a covariant family. Or if I'm doing it the other way around, it should give me back the identity. But then of course there are, those are separate proofs.
Yeah,
but then again, one direction is trivial because if you're lifting the identity, you just get back the identity. But then the other direction, that's not so trivial, but it basically comes down to some naturality properties and covariance of this here, yeah, so we have a paper about this for anyone who's interested in that particular aspect, but I'm also of course happy to talk about it some more whenever people want to. But that is this paper, and actually in the repository for this project we have a contributed formalization by Sina Hajratpour, who's also at Johns Hopkins, for the Unida lemma for one categories in lean, and his proof is more, I mean, he has to do some steps that we don't have to do because the language just takes care of it.
Mm-hmm. Yeah, maybe just a related question. Why did you need the NU proof assistant? What are the peculiarities that you couldn't,
Yeah.
take care of in other proof assistant?
Yeah, that's a great question. So, of course, the theory of infinity categories, I mean, there's extensive literature. I mean, there's like tens of thousands of pages, but they're all essentially working with set theory or with some kind of unspecified, quasi-informal, quasi-formal, mathematics. So, of course, one could go ahead and try to use lean, right, and formalize, I don't know, first 100 pages from Lurie's higher topos theory or something. But this is very heavy category theory. And I think there are some formalizations on the way where people are trying, but it also uses a lot of things from model category theory, from homotopic algebra. So, and ultimately, I mean, you would have to do a lot of work kind of in set theory to do even basic work on infinity categories in the formalization. So the point that I'm making is that means if you want to circumvent that, that means you have to come up with a new language, with a domain-specific language for infinity categories. And for a long time, there didn't exist such a language up until Emily and Mike wrote their paper, published in 2017, or at least uploaded as a preprint in 2017, published somewhat a bit later, I guess, maybe not too much later, I don't know. But that was when that came around. And but there was no proof assistant that supported that language, and RZK is the first one that does that. There are some other projects that are somewhat similar and that have some parallels, but that are not quite the same. And some of them differ in that it's not clear what they mean semantically. So there is some work very similar to a lot of things I told you about in some kind of cubicle type theory, bicubicle type theory, actually, due to Matt Weaver and Dan Licata. But there semantically, it's not clear, to my knowledge at least, if that really models infinity category theory, because they're working in cubicle space. So they have like cubicle versions of these Siegel spaces. And these cube categories from a homotopy theory point of view are much harder to understand. And it's not, it's not clear. The landscape of the homotopy theories that they model is not clear. So it's not, so you're doing something internally that kind of looks like category theory, infinity category theory, but you don't know if the actual semantics actually coincides with what people traditionally think of infinity category theory. And the other kind of difference is that in some of these formalizations that are similar, people don't quite work with the same level of strictness that I'm doing here, that we're working with here. So I mentioned these extension types that kind of allow us to do to define hom types and all these things. And the intricate thing about them is, I mean, why do we even have to introduce them as extra types? The point is that they capture these. If I have a type family over like a big shape and I have a smaller shape and a section A of that type family defined on the smaller shape, I'm interested in all the extensions B of that small section, but I want the extension to be strict and not just weak. So whenever I have a type here, whenever I have a term here, this is like a pi type, like a dependent function type, but with a law that describes its behavior on the boundary, on the kind of boundary in a strict way. So it's like a pi type with strict side conditions. So if I didn't have that, and Emily and Mike, as some other people did, I think initially tried to just to start with an interval, okay, without these like strict extension types. But then it turns out you run into a lot of coherence problems like pretty early on. Like even if you just want to prove associativity of composition in these Siegel types, which are kind of like infinity categories or pre-versions of these. So if you just ask for a path here, an identification, instead of a strict equality, things would just be much harder. And a lot of these theories, kind of like Agda or other. I mean, maybe I shouldn't say too much about these implementations because I don't, I don't want to get out of my league here, but there was no, so I think some of these formalizations, they kind of tried, with like weak equality here, but then it just turns out very complicated and people didn't get too far. But here, this is an example of a theory where we did a lot of work on paper for a few years. And then Nikolai, at some point, I mean, this proof assistant, he started developing it kind of a few years back already, but it was only kind of at the beginning of last year when we prompted him to said, oh yeah, we actually want to use this to formalize some things from the real Schulman paper and then some of my follow-up work. Can you help us, or can you, what feature, we might be interested in having this or that feature, and he's implemented so much since then. So we have a library that now contains proofs of most of the main theorems from the real Schulman paper, not all of them, but a lot of them. It contains some improvements. It actually helped spot a bug in the paper, because at some point the paper in the proof used the circular argument. And Emily herself tried to, she wanted to formalize a theorem that used that result. And so she basically, I think, just copied the proof as it was in the paper. And it was about showing that some type is Siegel. And then in the proof, so Siegel means having this composition. And in the proof, it says, okay, because A is Siegel, we can do this. But of course, you don't know that A is Siegel. It's exactly what you want to prove. And so the proof checker said, okay, you don't have an inhabitant of that like you don't know that this proposition is true. She was like, ah, okay. And then she managed to fix it. So together with Mike, they put out an update. So it wasn't like, you know, at the end of the day, it was okay, but it was false that it was written down. So that was definitely a, you know, a big virtue. And to even develop all these theorems from the paper, we of course had to use a lot of standard results from homotopy type, just standard homotopy type theory, which has been formalized in a bunch of proof assistants and a bunch of libraries. There's an abundance of kind of many proofs from this homotopy type theory book that I mentioned at the beginning. But of course, this didn't exist for this proof assistant RZK. And so we had to go ahead for a while and kind of just redo the work from just standard homotopy type theory in that library. And that's also, I mean, you can also just use this proof assistant as a, you know, just for standard homotopy type theory. It's not like one forbids the other, like it's a strict extension. Yeah, but it's probably not the most, for that purpose, definitely not the most user-friendly implementation. So you might want to look at other libraries for that, like Cockot or maybe Agda Unimath.
Other questions? Okay. I had just a comment, and it is that when you mentioned the Leibniz principle, I always heard it the other way around. So when I heard the Leibniz principle is that if two objects are indistinguishable by a property, then they are the same. And the property that you mentioned is just a substitution invariant. If two things are the same, then they should have the same properties.
Okay, that's, yeah, so I agree with the substitution invariance. I meant if, you know, someone with the competence in philosophy would like to have something to say, I'd be very interested to hear, but
Depends who you
I would,
ask.
yeah.
Which the kind will, it depends who you ask.
I see.
Depends on how Leibnizian the philosophy is.
Okay.
What you just mentioned was identity of indiscernibles.
Identity of indiscernible, yes. Is not the Leibniz principle of the identity of indiscernible?
Sometimes I understand Leibniz principle as the way it was presented.
The way that he presented that two things are equal, then they have to have the same
Leibniz did
properties.
everything, I think.
Okay. Okay.
They're both.
These are subtleties apart. The problem with the Leibniz principle is that already Leibniz apparently stated this principle for anything except a mathematical object. And the point is that in mathematics, this principle is clearly false. So I continue not to understand how we can base a foundational theory of something like that. There are a lot of literature of this. Take the case of any non-trivial automorphism on a structure, and of course you have a problem there. For example, I and minus I in the field of complex number, of course they are indistinguishable with respect to their property. But if we do not distinguish them, we cannot make complex analysis. But 1 is minus 1 in the group of an additive group of the relatives also, of course they are indistinguishable. But without distinguish them, we cannot make even arithmetic. So that seems to me a real problem, because we need to distinguish indistinguishable objects in order to make mathematics.
Thanks, Marco.
Yeah, thanks for that comment. So as I said, I'm not claiming this is the one theory to rule them all, but for something like homotopy theory or homotopical mathematics, definitely saves a lot of pain. Oftentimes, having this homotopy invariance built in. But I'm not making the claim that this is all of mathematics. So
yes, I like that.
Yeah.
Any other questions?
Yeah, with the infinity category, you're telling us to think of it as a space. So I'm having trouble understanding it as a space, but you can tell me how I can understand it as a space. Because the starting point's a category. As you iterate this procedure, like you have a 2 category, a 3 category, a 4 category. But the thing you start with, the way I'm picturing it is, it's a category which is, this might be my problem, but I'm picturing that a starting point is like graph structures, like diagram. So how do you get a continuous space out of this initial starting point of diagrams?
Yeah, the point is that that's a great question. So the point is that somehow the topology is already given to you. It's and a category, it's something that is strictly more general than a space, I should also say. So as per Grothendieck's homotopy hypothesis, every space can be regarded as a category, in the sense of that so maybe this is a space S, or yeah, maybe this is a space S. So what's a space? It should have points, and those points should have paths, like that. And then the paths, they also might have relations. So I might have a homotopy, and homotopies are always reversible by reparameterization. So I can just draw in like this equality cell here if I want to. And then of course this also, you know, might have some cell, and then there's some higher homotopy, and so on. But when we're doing this, when we're interpreting this more algebraically, then essentially this is exactly what an infinity groupoid is. And in fact, you have to be a bit more precise. So ideally, you would get an equivalence of categories, like you have topological spaces, and then you have infinity groupoids. And you do have such an equivalence. And it's not just an equivalence of these categories in the sense of, okay, you know, kind of, it's a relation between the objects and the hom objects and whatever. But you actually, you can impose what's called a model categorical structure on both of these categories. And the model categorical structure is a way to model the homotopy theory. So what are the fibrations? What are the good inclusions? What are the weak? What are the homotopy equivalences? And you have, and that gives rise to the notion of Quillen equivalence. So two model categories are Quillen equivalent, meaning that they model the same homotopy theory. So I mean, it's a very technical notion. I'm not going to define it, but you have such a Quillen equivalence, and that means the homotopy theories are the same. Same homotopy theories, and well, I guess the question. So I mean, this is of course kind of informal, but if we try to make this more formal, or if we just stick with the informal picture for a second, we can now ask to have arrows, you know, that maybe are not all invertible, but they have composites or something like this. So that's kind of intuitively what an infinity category should be. And I mean, I haven't really said what is an infinity groupoid, and I also haven't said what is. I gave you some intuition of infinity category in the set theoretic case, but I haven't actually given you what exactly is the definition. So I've said, okay, roughly it's something like this. Then I gave you some internal definition, and I've said, oh, this internal definition interprets to the right external set theoretic definition. But I haven't given you the set theoretic definition. But kind of one definition is like using simplicial sets. So and then you would say an infinity category is a presheaf. So it's a functor from a certain category delta and the opposite of that to sets. So it's some kind of family of sets, and delta, that's the category of finite ordinals, and you can think of this as the kind of category of simplices. So zero simplex, which is just the point, the one. So delta 0, delta 1, that's the arrows, and then you have delta 2, which is the the filled out triangle. And then of course you have some relations between these simplices, because like the point can include into the arrow, and the arrow can include into the two simplex, and the two you can collapse, you can degenerate the two simplex to an arrow and something like that. So you have some maps between those, and that's essentially what the category delta is. And yeah, and so these simplicial, and I mean that's a functor category. So that's the category of simplicial sets. So set to the delta op, or S set. And infinity groupoids and infinity categories are both simplicial sets that have a certain that have certain properties, certain lifting properties that will essentially give us these composition operations. So in this model, they're really objects of the same category, but the condition to be an infinity category or quasi-category, that is weaker than of being an infinity groupoid. So in this model, the infinity groupoids are called the Cantor complexes, and the infinity categories are called the quasi-categories. And this is not quite the model we're using for simplicial type theory, because here somehow the quasi-categories are, somehow we want to have an infinity topos where the quasi-categories themselves embed, which we can't do here. So we have to replace, to come to the Siegel space model, we have to replace sets by simplicial sets, which gives us bisimplicial sets. So it's simplicial diagrams in simplicial sets, or alternatively, it's bisimplicial sets, which are sets from, which are like objects, which are objects from delta op times delta op to sets. So that's what I meant with it's a kind of two-dimensional space. So this means that. So looking at diagrams of the form delta op to some C, where C is some category, means looking at objects in C that depend on simplices, but by the Unade lemma, depending on a simplex means that you can map into the simplex, right? So like xn essentially is the same as mapping from delta n into x. That's the Unade lemma. So, so that means that maybe it's not so great to call this fun, but whatever. It's like, yeah. So you can think of, it's a very classical idea of topology that you can triangulate a space, right? At least a well-behaved space. So you have these simplicial complexes or cell complexes, and that is a more combinatorial version, because you just in the easier version you're just taking sets here, right? And one can also show that this, what I wrote here, this equivalence up to infinity groupoids, it's really the model, model structure. Model structures are also not unique, so you have to be careful, but it's kind of the homotopy theory over the standard homotopy theory of topological spaces coincides with the analogous homotopy theory for these Cantor complexes, which are combinatorial replacements of spaces. So in that sense, I'm really thankful for your question. In addition, because I should really say, which I haven't said before, but I really should say, okay, I'm implicitly working in a model that already is a combinatorial replacement for, the topologist notion of topological space. But for the homotopy theorist, these combinatorial, the Cantor complexes or whatever, something like this, they're often more, they're kind of often better because it's a combinatorial thing, it's more discrete. And ultimately it doesn't matter because we have this Quillen equivalence. So that would be the unifying picture. Again, not quite that, but rather like the bisimplicial version of this, but that's the basic intuition. And simplicial homotopy theory, I mean, that's a very, goes back to the 50s and probably earlier, to be fair, but there's a lot of literature on that as well. And if you're looking at that literature, I mean, these conditions, you know, typically they would involve, if you spell them out in terms of the target category set, it's something infinite dimensional. But if you write them down in terms of some internal exponential, it again becomes something finite, which is also something we haven't, or at least it does in the infinity one case.
Okay, then let's think. I'll speak again.
So